In this segment, we're going to look at problem number 6 on circuit analysis worksheet number 1, and kind of take some time to work through this and look at exactly how to do a circuit analysis on the most complicated one on that worksheet. And you'll notice that it's really a combination of numbers 4 and 5. So when we're analyzing a circuit, we got to start out with simplifying everything down to our total voltage, current, and resistance. And looking at this, we are given 15 volts at the power source. That's our VT. Okay, so our VT equals 15 volts. Now, in order to get the total current, our IT, we know that V equals IR, and so I equals V over R. In this case, it's IT, and so it's simply IT equals VT over RT. And so we can do that really with any of the components. So in order to find the total current, we need the total resistance, or as we sometimes call it, the equivalent resistance. And let's start at the far end, and we always look at components that are wired in a similar type of circuit. And so if we start on the far right, we have these two components right here, the 5 ohm and the 7 ohm resistors. That's resistors 5 and 6, and they're wired in series. And we know in a series circuit, we simply add the two together. And so in this case, the equivalent resistance of these two is going to be 12 ohms. And so that simply means that we could replace those two resistors with one 12 ohm resistor, and the properties of the circuit would be exactly the same. So let's quickly let's redraw our circuit now. And so we have here's this component here, or these two. I'll go through this quickly. And then we have our resistor here. Now let's imagine that we replace those two there with our 12 ohms. This is 4 ohms. We have our 2, and we have our 3 and our 6. 3 and 6 ohms. Okay, so now we have, again, we'll just stick to the right. We have our 12 ohm and our 4 ohm resistors in parallel. And remember that we're talking about in parallel. 1 over RT is equal to 1 over R1 plus 1 over R2. And so if we plug this in, it's 1 over 4 ohms plus 1 over 12 ohms, which would give us what? Right, so we would get 4 over 12, and since that's 1 over RT, RT would then equal 3 ohms. So now we have an equivalent resistance here of 3 ohms. And so we're going to keep redrawing this with our equivalent resistors. You certainly don't need to do this when you're working through these problems. This is just kind of so you can see. And so this is the equivalent circuit, where this is 3 ohms, and this 3 ohm resistance represents those resistors 4, 5, and 6. That's the equivalent resistance. And so again, we have our 2 ohms, 3 ohms, and 6 ohms. The next step here, the next easiest two to combine, are going to be resistors 2 and 3. They're in parallel. So again, we're going to say 1 over RT is equal to 1 over 3 ohms plus 1 over 6 ohms. Take a second, and you're going to get, right, so here we're going to have 2 6 plus 1 6 equals 3 6. We have to take the reciprocal because it's 1 over RT. So that's going to give us a resistance of 2 ohms. So those two have an equivalent resistance of 2 ohms. And now we're going to have, again, our 2 ohm resistor here. Our equivalent resistance that we just found of 2 ohms. And then our 3 ohm equivalent resistor out here. And again, this is 15 volts. Now we have these two, which we add them together, and that gives us, right, 4 ohms. And so we can actually, we'll just do this, replace that with 1 resistor of our 4 ohms. Now we just have 2 resistors, so we're going to add those together, add these two together here. They're in parallel, so we're going to do 1 over RT equals 1/4 plus 1/3. And when we add those together, we're going to end up with a resistance of great, 1.71. So our total resistance, or our equivalent resistance for this entire circuit that we started with, is 1.71 ohms. Now that we have our total voltage and our total resistance, we can calculate our total current. And again, remember that V equals IR. So our IT equals total voltage over total resistance, where here our total voltage is 15 volts. Our total resistance is 1.71 ohms, which we just calculated. And so that gives us a total current of, good, 8.75 amps. Now once we have that, we can start working back through and calculating all of our other components, our voltage drops and our currents through each of our other components. So now we come back to our main diagram. And so we now see our total current is 8.75 amps. And I've also labeled the resistors with their numbers to help us identify each one a little bit better. You also notice we have VA, VB, and VC. And those are the voltages across each of these paths, because we should remember that in a parallel circuit, the voltage drop across each section of the circuit is going to be the same as the total voltage. And so our VA here, our VB here, and our VC here should all equal volts. So now we can start looking at their individual currents. And if we start on the far right, on this section here, through 5 and 6, through these two sections here, the voltage across that section is going to be 15 volts. But we know that that voltage is then going to be divided across those two. So we want to find the total current across that section. So in order to do that, it's going to be, again, V equals IR. And in this case, it's the voltage across 5 and 6 equals the current through 5 and 6 times the total resistance of 5 and 6, which, remember, we just add them together, and so that's 12 ohms, So our current through that leg of it, through this portion here, is I equals V over R. In this case, our voltage is 15 volts. Sorry, it's getting a little messy. And our resistance is 12 volts. Okay? Now, if we do the math there, we get, right, 1.25 amps. And so our current through this portion of the circuit is 1.25 amps. And we remember that in a series circuit, which these two are, the current is the same. Good. And what that now allows us to do, we're going to move this over here a little bit, and let's, yeah, we're not going to be able to move that. Let's try moving that. There we go. Get that out of the way. So now if we want to find the voltage drop across each resistor, so let's look at the voltage across 5 is going to equal the current through 5 times the resistance of 5, which in this case is 1.25 amps times, running out of room, 5 ohms. Okay, which, when we do the math there, we get 6.25 volts as the potential drop across 5. Now we can do the drop across 6 in two ways. We know that in a series circuit, Vt is equal to the addition of all of the voltages, so on and so forth. And so we can just do 15 minus 6.25, or we can use the potential across 6 is equal to I6 R6. Either way, we're going to get a potential drop across resistor 6 of 8.75 amps. Okay, and so we see added together, that gives us our 15. So this plus that, whoops, sorry, I said amps, I meant volts, of 15 volts. Now through resistor 4, we take this down here. Again, we know the potential drop across that. The voltage across 4 is equal to 15 volts. The resistance is 4 ohms. Okay, so calculate that real quick, and what do you get? Okay, you should have gotten a current through that portion of 3.75 amps. Okay, so that is the current through 4. So we come up here. Let's do this here. Now our current, our current through this second portion is, as we said, 3.75 amps. Now with these two, that we know the current through this path, and this path have to add up to our 8.75. So we have 3.75 here, 1.75 here. That gives us 5 amps between these two sections here, which means that the current through this path A has to be the difference, which in this case is 3.75. So our current through A, through path A, is 3.75 amps as well. It just happens to be a coincidence in this case. Now if we know the current through A, we know that the current then through resistor 1 is again 3.75 amps. And so we can calculate the voltage drop across resistor 1, V1, equals I1 times R1, which in this case then would be 3.75 times 2, and that's going to give us a voltage drop across resistor 1 of 7.5 volts. And so that's 7.5. That means that the potential drop across, whoops, there we go. The potential drop across these two against the other two, across these two, then has to be the same, 7.5. And if we know the voltage drop across each of those is 7.5 and 7.5, then we can find the currents through each of those, again using, so I2 equals V2 over R2, and I3 equals V3 over R3, and that's going to give us an I2 of 2.5 amps and an I3 of 1.25 amps. And you can see again I2 plus I3. Okay, so this one right here plus this one right here is going to add up to give you the total going through that, which is the 3.75 because it's split. Now, this is a long one, it's a complicated one, but it's really just breaking it down step by step. And if you break it down step by step, anytime you analyze a circuit, it really should be, the process should be easy. It sometimes might be a little time consuming, but the steps themselves, each individual portion, shouldn't be that difficult because we're just working with a 3-variable equation. Great.